Well, I have a big one here for the weekend. Kind of been waiting to talk about it until I had enough evidence gathered and so forth. I think I've known for quite a while, and I've given some hints, but I kind of just wanted to wait until I had enough to show you. And so this video is going to take you through to what I believe is the size of the capstone of the Great Pyramid, what the size of it is, and kind of what it means. Or I can touch on what it means, but I've found that a lot of the stuff that they show will typically have multiple meanings. But I think by the time this video is over, you'll have a much better understanding and kind of the reasons why things are the way they are. What you're looking at right here, what I wanted to do is, I'm a very visual person. I don't like to just talk numbers. People talking numbers to me, that just bores me to death unless I can see what I'm talking about. And that's kind of the way I am with, and that one of the reasons I like geometry is because I can actually see what's happening. And of course, when you watch this geometry build on itself, and then you visualize kind of a universal picture, it makes much more sense than it does when you're just talking numbers. And then of course you realize that some of the things that they tell you in mainstream science are not necessarily as important as you thought they were when you're dealing with subjects like this one. Simply because it doesn't matter if you're talking about pi to the 100,000th digit. It makes no difference. It's an irrational number. If we wanted exact measurements, we wouldn't have irrational numbers. We wouldn't use irrational numbers. So you have to just pretty much decide how exact do you want, and how much do you want to sacrifice for that. Because some of it has to do with showing harmony among numbers, which is kind of what I'm going to show you here. And I'm going to kind of show you where pi kind of starts to fail in this area. A lot of people have given these guys hell about the pyramids because they used they squared the circle using the 11 and the 14 system. But actually it makes much more sense when you know what they're doing, because when you're talking precession and you're talking numbers associated with precession, well, not only that, if you take a look at this graph right here, this is kind of the 11-14 thing I've got going on here. So if you look at these two triangles here, they're right triangles. This grid I've set up to show you this. So this is 11, this is 14, and then these are the two that I've shown you so far. These two angles I'm always showing you with a sphere right there. So that's what these are. So we have one where we have 11 over 14, and then we have 14 over 11. So if we take the tangents of those things, so this is the ratio, if we take the arctangent of that, we get 3816 and 5184, which come out to pi over 4 and the square root of 5, which are basically reciprocals of each other. But you don't ever hear anybody talk about that. They just talk about pi over 4, and they talk about the square root of 5, but they never really visualize it for you and show you the reciprocals and why it's important and how it comes into play in the squaring the circle thing. So the system that we have, or the 360-degree system that we have, is not as crucial in this particular system, because in this system you're dealing with precession numbers. Which are all based off of like a circular number. A lot of them will, most of them, and not all of them, most of the factors will have digital roots of 9. Okay, this is not the case with like the 360-degree circle. You have 1 degree, but then it's the 3.14. In the system of what I'm talking about here, for example, if we wanted to get to 51.84 degrees, we could divide the circle up into, say, 500 degrees, right? Where each degree is equal to 0.72 degrees. So each one is equal to 0.72, okay? And so then if we want to get to 51.84, it's 0.72 times 72. So this type of thinking also works with precession as well. It doesn't work with precession when you use just standard 360-degree numbers. So that's another reason to use it. If you take a look at the graph here, it's extremely simple. You can see where I plotted these things and I put them in each quadrant. So these little red dots up there at the top, you can see where the square is supposed to go through the circle. So it's about as easy as you can get, and you can visualize it, you can plot it, and so you can see what the angles are, why they chose them. But the 5184, and numbers like that, these are also precession numbers. And so a while back when I was talking about Stonehenge, I was also mentioning that it seemed like they were using distance in relationship to angles for some reason, if you remember, because they used a 360-foot diameter circle, and they used 5. I mean, of course, you could divide 72 up by 5 to reach one side of the circle or the other. So they were showing a relationship between angle and distance. Well, there's really no such thing, I guess, as distance, because really what we're talking about is size. So if you're talking about the universe, you're talking about the size of various geometry, whether it be a sphere or whether it be a square or whatever it may be. But it's just the size of those things. They're different polygons. Something isn't necessarily far away from something else. One thing is just much bigger than something else. Manly Hall goes into this as well. But okay, so you've seen this. So now let me kind of show you some stuff about the numbers and why it makes a lot of sense. If you remember the last time I was showing you this thing on the 10 degrees, it was the thing I had been looking at, but I hadn't come to a conclusion yet. So I've got a lot more information on that now. So when we start talking about precession numbers, but I'm no precession master, but I know enough to get me by. And I know enough to look at patterns and be able to recognize things. So we have two different types of circles. We have one that has factors of 14. So if you notice the 756 circle, the larger circle has 22 factors, but it has 14 as a factor, where the 594 circle, which squares it, is an 11 circle. Okay, so it has an 11 factor in it. So when we put the 594 inside the 756, then we naturally have something that we can plot. It's easy, and it works in with the factors, and these factor numbers are important because this is what we're going to be looking at when we look at the precession numbers. Okay, and why? And you're going to see where it makes much more sense to stay away from pi as we know it. There's other versions of it that are okay, but as we know it, it's not helpful in a lot of areas. So let's take a look at what I was showing you last time, this whole thing with 10 degrees. So first let me just show you a quick picture of what that looks like. It looks like this. Okay, so we have a circle here. I know the circle's diameter. The circle's diameter is 594. Okay, so in order to find out the circumference of this circle without using pi, I use a certain ratio. So I divide 594 by a certain number. Since it's an 11 circle, it has a slightly different ratio than the 14 circle, but there's only two. Okay, so we have one we use with the 11 circle and one we use with the 14. So once we divide it by that ratio, then we can take 36 of these circles, put it around this thing, and then multiply them by 36, and you get your circumference. Now it's not to the 100th digit like pi, but the difference is that it is consistent, it works in harmony, and you can find what you need in the list of factors and precession numbers, so you can see the relationship to the other pieces of geometry that you're looking at when you're trying to look at the whole picture. So the difference between pi and what you're and this method here would be the difference of the tree versus the forest. If you want to look at the tree, you use pi. If you want to look at the forest, you use these other methods that they were using a long time ago, because they show you the harmony among things more. where you're in pi, if you're using pi to the 100th digit or whatever, you're interested in some exact measurement of one thing, but it doesn't give you any information about the other things, because when you start putting it together with everything else, it turns everything into noise. Okay. All right, so we'll come back to this, but I want to show you just some numbers real quick and how it works. Okay, so if we use the 360 diameter circle, then we divide it by this ratio right here, 11.4583333. This is what we get. If you notice, we get the 31.418181818. This 181818 number that they were using for pi a long time ago, or so it turns out that we have discovered this, it comes from precession stuff that they were doing. I'm almost positive it does, and it comes from geometry as well. So because they were using geometry, and of course when you mess with the geometry and you're trying to make things work with each other, you find that this is what comes out, this right here. So you take that number and you multiply it times 36, and this is your circumference, or the 360 diameter circle, right? We never used pi. Now here's what happens if you multiply 360 times pi, you get this number. And so if you divide what you get by pi versus what you get here, this is how close they are. So there may be some people out there that say, yeah, but you might need that 100,000th percent or whatever. That I beg to differ when it comes to stuff like this. I think it becomes useless because you need a harmony. You don't need something exact when you're trying to look at a whole picture. So here we go. Here's some examples. So the square root of phi is one of them. Of course, this version of the square root of phi is using the 11 and the 14 numbers, right? So this is actually 14 divided by 11. And so you divide that by 11.454545. Now the 4545 number is when you're using a 14 circle. Since we're doing 14 divided by 11, then we're using the 4545. So if you know, I want you to notice how clean the numbers are that come out when we do these this way, okay? Versus when you do it with pi. So this is the number you get. I've highlighted them in red. You multiply that times 36 and you get basically 4,000. So if we were to take that same number and we were to say 1272727 times pi, so you can see there's a huge difference in how clean they are. So here's the next one. So we have pi over 2 divided by the square root of 2, right? So this diameter right here is actually it's actually referring to, if you take pi over 2 and you divide it by the square root of 2, you get this number right here. And I've shown you this in geometry before. If we take this particular square and we turn it on its corner, we get pi over 2. When it's just not turned on its corner like a diamond, it's this number. So we divide it by that and we get 97, right? And so if we multiply that out, we get this number versus this number for pi. Now here's the pyramid numbers, and this is where this is really making a difference as far as the way things look. So a 1512 is a 14 because it's twice 756, and 756 is a 14 circle, right? So we use the 114545. This is what we get. Basically, I mean, it's 132. And we multiply that times 36, we get this. This is what we get with pi. Noise. 1188, which is twice the 594, and it's what squares the 756. So now, since it's an 11 circle, we use the 4583, right? So we take the 1188 divided by that, and we get 10368. Look how clean it is. And then this is our circumference, and this is what it looks like with pi. So here's the pyramid side length times the square root of 2. So this is the circle that surrounds the corners of the Great Pyramid, and that is a 1069.2 divided by, and since it's an 11, since it has a factor of 11, we get this. These numbers I'm showing you here, I'm going to show you in a minute too because they're important. Then we have the 756 number divided by the 4545, and we get 66, almost exactly, which means we get 2376 as its circumference, and this is what pi gives us. Useless. So then we have, and not only that, 2376, so if we take 2376, and divide it by 2, we get 1188. So you can instantly see harmony now between the 756 circle versus the 594, where it's rough to do that if you're looking at all those numbers with that decimal. Because if I take 1188 and I divide it by 2, I get 594. So you can instantly see now the harmony between this way of doing it. So here we have the 594 divided by that this particular ratio, and we actually get 51.84. Their circumference is this times 36, and what is that number? It's the 186624. Now here's what I wanted to show you real quick, and then why pi begins to fail. Okay. So when you're dealing with precession numbers, you need to be able to find a way to get to the precession numbers so that your geometry makes sense and so that everything can make sense. If you don't know what you're looking at, as far as these different factors over here I'm going to show you, then these numbers, you can take a guess, but it might be something else, right? Not only that, I can use these kind of things as check digits because a lot of times, or at least most of the time, they have digital roots of 9. The 186624 adds up to 9. 5184, 6 plus 12 is 18. 1 plus 8 is 9. So they add up to 9. Okay, so you get these ways of checking yourself, which is you can't really do here. So here's what happens. So if I take the 186624, drop the decimal because we're not interested in the decimal because we want to look at the factors. So 186624 versus 1866106, and so this is what it looks like. So if we look at the 106 that pi gave us, you can see that it gives us nothing of value at all. But if we take a look at the 186624 number and we start going through these numbers, well, look what we're looking at. We see 9312, that's right here. We're familiar with 132 because that's twice 66, right? But we have 10368, that's in here. We have 5184, that's in there. We have 20736, that's in there, right there. So as you can see, these numbers, and if you take a look at these numbers here in this 186624, this is a manifestation of Brahma right here, which is a huge number. It uses these particular numbers. This is the distance of the moon from the Earth in miles. You have the 1296. Obviously, that's a big number. The 25920. So these types of things right here show these are precession numbers. Okay. And then, of course, you get the 432 squared. And then also at 186,624 is the speed of light in miles per second. Now, another thing about all this is that I'm not aware of the measurement in meters in harmony with precession numbers like this. Unless somebody can correct me, I'm not seeing it. The numbers are in feet, at least for the Giza complex and things like this, the 10368. Because the middleman here is the degrees, right? So if the degrees, which are dimensionless, dimensionless unit, right? We're not talking about a foot or a measurement. We're talking about a degree. It's dimensionless, but yet it is in harmony with feet, not meters. So, okay, so that's the reason why we use these particular things. So I wanted to show you something real quick because I mentioned something about the sun. The sun is 864,000 miles in diameter. The moon is 2,160 miles. Okay, so we're talking miles and feet. We're not talking kilometers, right? Let's take a look at something in reviews. This number right here, 23328. All right, so if I take 2160 and I multiply that times 108, I get 233280. Okay, so now let's take a look at something real quick. I showed you this a while back, and everything is scaled down because I wanted to show you what this looks like visually. But the numbers are there, right? It's just the decimal place is smaller. So we have a 7.920, which represents the diameter of the Earth. So it's basically 1,000th of what it should be. So this should be 7,920. And then this right here, the size of the moon, is 2.160. So if we take this moon here and we move it vertically, and let's just go up here real quick and get this guy out of the way. And so let's come back here and we're going to move that moon vertically 2.16, because that's the moon's number, times 108, which is going to be 233.280. And we hit that. Okay, so there it is. It's right at the same level as where the moon is. Now if I zoom in on that, you'll notice that this ray perfectly covers both sides of the moon. The moon is a 1/2 of a degree in angular diameter from the Earth, and it exactly covers, or almost exactly covers, the sun. So the sun, now that's one of your precession numbers, and we actually had a couple, right? We had the moon size, and then we had the 108, and then we had the 23328, right? All those are precession numbers in that 186. So here's a couple more, all right? So if we take this and we zoom out, and the Earth is down here, and we move all the way up, then if you consider Earth being inside the middle point of a huge circle, right, whose radius is whose radius is 93,312,000 miles. And at the end of that, we have the sun. And if you notice, the height of this particular ray from the Earth to here is 93,312, which is one of our factors in that. So 93,312 multiplied times 2, which would be the diameter of this huge circle, is 186,624. So now I've given you all of these precession numbers here, and what we're really talking about is geometry at a very large level. Okay. So I'm going to go ahead and make a part 2 on this real quick, give everybody a break, and I'll be back in a few minutes.